An hour and a half, yeah. Do I need a mic or something? I can project my voice, I guess. Do I need it? I don't know for the recording. I don't think I need it for the room. Certainly for the room, it's small enough. Do you want to give me the one that I can carry on? Yeah, that one.
Test.
It's a good way to put this. It's fine. And I can keep this. Test, test, test. Are we good to go? All right. Welcome, everyone. So let's get started. Thank you very much for coming to my tutorial. My name is Semih Salihoğlu. I'll introduce myself in a second. I just want to say, okay, so the title of my tutorial is Beyond Relational Data Systems for Knowledge Graph Applications. And as I will elaborate in the tutorial, the term knowledge graph, it's an umbrella term that's used by developers of certain applications to refer to certain data sets. And different communities mean different things with this term knowledge graph. And similarly, I'm using the term beyond relational data systems to this term beyond relational as an umbrella term as well to refer to several classes of systems that are they extend relational systems and that are different from the traditional relational systems in some sense. And as I will say, one of the commonalities of what people refer to as knowledge graphs is that the data systems that people use to actually build applications they go beyond SQL, beyond these traditional relational systems. So that's the umbrella term that I am using. So this is a very kind of a technical talk. So it's really assumes a developer or technical audience. So, and it also assumes that it's going to cover three classes of systems: data log, property graphs, and RDF. So it must be the case that you don't know one of these so that you'll get something out of this. So if you know these systems already, this might be the right time to maybe switch to another tutorial. So that is what you're going to get out of this basically. I'm going to try to provide you a framework to how to look at these three classes of systems and why people use one over the other, right? And also upfront, I'd appreciate taking questions as we go along. It's going to be, I think, a lot more productive if, I can answer the questions that I raise. So please stop me at any point in time. All right, so let me just tell you a little bit about who I am. My name is Semih Salihoğlu. I am the CEO of Kuzu Inc. This is a startup commercializing the Kuzu property graph database. I'm also an associate professor at University of Waterloo in Canada. I work on database management systems, and specifically within database management systems, my expertise is on what I'm broadly with this umbrella term referring to as beyond relational systems. So, this is my university website, and you can see, for example, I give seminars with the same title, Beyond Relational Systems, PhD seminars, also PhD seminars on knowledge graphs. These are the topics that I generally work on. So I work on basically systems like property graphs. I work on systems like RDF systems or data log logic-based systems and things like that, things that kind of go beyond the traditional ad hoc relational systems. And all of these material, a lot more depth you can find also from some of these seminar readings that I have on my university website. All right, and so this is going to be a vendor agnostic kind of talk. I'm not going to really promote Kuzu particularly. It's one of the property graph systems that you can use, but I do want to plug in a talk about Kuzu, or that uses Kuzu, a collaboration with Sensing, the Sensing company, and Kuzu. That will be at 11 a.m. today. 215, I think, is the room. And that there, Prashant, engineer with SPARQL, who is also here, will be speaking about constructing high-quality knowledge graphs from unstructured and structured data. So if you want to learn more about Kuzu in action, etc., please go to that. And we'll be here throughout the week. Three of us, Ardan, my co-founder, and Prashant and I were here. So I'll leave kind of evangelizing Kuzu to outside of the tutorial. All right. So let me start with this. So here's a lightning fast history of different classes of database management systems. Even though objectively relational systems are the most widely adopted systems, that is at the core of many enterprises. Even prior to relational systems, there were classes of software systems we call database management systems. So here is a picture of someone named Charlie Bachman. He is credited as the first sort of inventor of database management systems. He's kind of credited as the first architect of the first software system that we call database management systems. He was the architect behind a system called Integrated Data Store, and that is what people refer to as the first database management history. And there's like about 20 years prior to relational systems hitting the market, where there were classes of systems like IMS, information management system, or IBM, still widely used actually in production. And then every decade kind of sees a different class of database management system that is produced. And I could say this sort of beyond relational systems, and more particularly graph-based systems that have a different data model than a tabular data model and different kind of properties in their query languages. They've existed all the time. And in fact, and this is kind of surprises people when I say, even the very first database like IDS and IMS, they had a graph-based or network-based model. The data model of, for example, the very first database management system in history, IDS, was called the network model. A network is just another term for graph. So the point that I'm trying to get across from this slide is that the class of systems that you could broadly refer to as graph-based models that adopt graph-based models have existed throughout history. Every decade, there's going to be a new class, and maybe the latest sort of one is the one that was introduced by Neo4j, the property graph model, but they've always existed. So this class of systems are very fundamental. So this is kind of what I want to get across. It's a very fundamental to software development, this essentially beyond relational systems, in particular graph-based systems. And here's just to convince you a little bit more. Here's a 1962 picture of an marketing ad for the IDS system. This was built at General Electric. And you can see nodes and edges and records being connected to each other with explicit relationships very clearly, even in this 1962 marketing ad for IDS. Right? So by no means, the point that I want to get across is that these classes of systems, at least the core some of the core features that you see even in modern systems, they might go back even 50, 60 years back to these very, very old systems. So it is very fundamental. They will also always be around as long as software development is around, right? All right, so in the very beginning of the tutorial, I kind of said, this knowledge graph means different things. It's an umbrella term. Let me back it up with a quote from Wikipedia. In the Wikipedia page of the article knowledge graph, it does says that no single commonly accepted definition of a knowledge graph exists. So that's true. So some people, for reasons that I never trace back, there's always a picture. This is, I think, the picture people refer to, people put when they talk about the Google knowledge graph, and it's always a picture of Mona Lisa and Leonardo da Vinci. I don't know that I've never been able to trace back. Why does everybody feel the need to put Mona Lisa and Leonardo da Vinci? Why these two entities in particular? So some people, especially if you're from semantic web community, I think it means something like this. Again, popularized around 2012, 2015, in those years by Google. To some people who come from a different kind of community, it might mean kind of another sort of more enterprise, common enterprise maybe data set that you model as nodes and edges. And to some people, if you look at the kind of old textbooks, and I don't think anyone does this from sort of crazy academics like me, you can read books about knowledge bases and knowledge graphs, and that people would have these like logic-based systems to refer to these class of systems. So this is a screenshot from Jeff Allman's knowledge base textbook from, I don't know, God knows how old it is, but in the 80s or 90s or things like that. Okay, so the different communities really use the term to refer to different things. Actually, a funny quote is this, in this textbook in 1990s, I think Jeff Allman refers to the term knowledge base and knowledge graph as I abhor this term. I really don't like this term. It's very confusing, etc. But anyways, it is kind of this confusion, I think, still persists. All right, but one commonality you can find across all of these different communities is that whatever it is that they're referring to as a knowledge graph, the data systems that they use to actually build an application, they're often not relational. They're not really building these on Snowflake. They're not really building these applications on Postgres. So they use some class of data system and this is why I'm referring to as this beyond relational in a sense, that has different features, different capabilities than a relational system. It differs from the relational system either in terms of its query language or in terms of the core data model. And so beyond, so one commonality you can find is that these developers, but when they say you got a knowledge graph application, they're usually using some of these other alternative data systems. So that's what I refer to as this beyond relational system. So what are the two sort of requirements that arise when people need to find a system that go beyond SQL systems? So the two key takeaways is that one core requirement that is common across these systems is often they require some kind of recursive querying, recursive computations, right? And this is kind of like the Achilles heel of SQL, is that there isn't an elegant way of performing recursive computations, say like path computations, etc. It's very ugly to do in SQL, and I'll tell you a little bit about that. And the second is that sometimes some kind of graph-based modeling or object-oriented modeling is necessary. And that's why these applications go. So this is kind of like the key motivation for what drives people to use some of these beyond relational systems for what they refer to as their knowledge graph applications. So this goal of the tutorial is to answer questions like this. When do these beyond relational requirements arrive? When do you end up kind of requiring some kind of recursive computation or kind of a graph modeling? And there's three classes of systems that I will talk about: data log, property graphs, and RDF. How should you think about them? What are different classes of these systems? And how do they compare with each other? So I could provide hopefully a framework for people to think about these three classes of systems, so you can position them and understand which one maybe is more suitable for you, for some of your application needs. And the non-goal of the tutorial is to cover any one of these in detail. I will be, I have to be mindful of the time, obviously. I'll cover three classes of systems. So none of them will I go it very deep, but I'll give you the core capabilities from sort of a data modeling and querying perspective. So that is kind of like the scope of this tutorial. And the upshot is that I'll form a table that looks like this. I'll have certain features that I think are important of these systems, and these sort of, for these three classes, this will be the table that I'm building throughout the tutorial. Right. Any questions? Okay, good. So here's the outline. So I'll go start by sort of a very sort of elementary motivation for why you would need something other than SQL. So why do you need to go to these beyond relational systems? Then one by one, I will cover the core sort of features of data log, property graphs, and RDF. All right, so let's get started. So I'll motivate the need to go beyond relational systems with an application from the finance domain. And so this is what I'll be assuming. And this will be kind of my running example. So suppose you've got a data set that you want to build applications over that consists of companies. And maybe for now, all you're storing is an ID for each company and the name of the company. And you've got these relationships about which company is a subsidiary of another company, okay, which one is a daughter of another company. And you got information about the stocks that are being sold as financial instruments, a stock ID and a ticker. And you got a relationship. This is, again, think of it as a conceptual kind of schema. Some companies issue certain stocks, and you got your customers who have names and phones, and you've got information about who invests, how many shares they buy from each stock. Okay, so that's the running example that I will walk through. Right? So in relational modeling, you'd take essentially each of these entities and these relationships and model them as a table. So your company table would be structured. So you'd structure all of this information into these structured records of tables. Company would have, for example, company ID and a name, or the investment relationship would have a customer ID, and the stock that this customer buys and the number of shares. Customers would have their names, phones, so on and so forth. And in SQL, obviously, you can answer certain questions, very suitable to answer certain questions that do data crunching over these records. So if you wanted to ask, how many shares did Bob invest in stock one, you could ask a SQL query like this. All you have to do is, the name of customers are in the customer table, what they buy is in the investments table, so you need to do a natural join between them, and you select on Bob and stock one. Okay, so that's it, and then you're returning number of one. But if you had a question like this, suppose your question is YouTube LLC part of Alphabet Inc.? Okay, so you could obviously write queries in SQL that kind of crunches the information in this company and subsidiary of relationship, right? So you got the company where you can understand that the ID of YouTube LLC is company 7, and to understand if YouTube is part of Alphabet in this company hierarchy, which is formed in the subsidiary relationships that you're holding, you can think of some kind of joins that you want to do over here, okay? But what you're really asking, if you think of this question, in the essence of this question, what you're really asking is this question. You're asking, is there a path of subsidiary relationships connecting YouTube LLC to Alphabet Inc.? That's what you're asking. So you're not asking directly for a direct subsidiary relationships, but you could be asking for a subsidiary of a subsidiary, subsidiary of a subsidiary of subsidiary. So the essence of the question is actually you're asking for a path between an object in your mind called YouTube LLC and an object in your mind called Alphabet Inc. So you're asking for, is there a path? And paths, by their nature, are recursive objects, recursive structures. Right? So you're actually asking for a recursive query. So, if you were to have a graph model of this information, you're asking, is there a path that is connecting YouTube, so that, to Alphabet Inc. And in this case, there's a 2-hop path. It could have been a 3-hop or a 4-hop path. Okay, so you're asking for something by its essence, by its nature, recursive. Right, so all the black edges here are subsidiary of, and I'm going to use black to refer to these subsidiary of edges. Right? Or similarly, if you were to ask this question, is Bob invested directly or indirectly in Alphabet Inc., right? So this may not be, super realistic sort of example, but again, if you're asking, answering this question, I'll comment on that comment in a little bit. If you're trying to answer this question in SQL, you obviously can, all the information is in these records. Your Bob is over here, the stocks that invests are over here. The companies of those stocks are in this stock relationship. Actually, I think there's an issues relationship that I missed. Issues relationship connect you to the company, and the subsidiary of kind of tell you this indirectness. So this question is asking not only if did you buy an Alphabet stock directly, but maybe a stock of a subsidiary of Alphabet Inc. So you're essentially, by its essence, again, looking for a path. You're actually asking for this, in your mental model, is there a Bob who invests in a company? And then is there a path from that company to Alphabet Inc. in this company hierarchy? Again, by its nature, a recursive question. And recursion in SQL kind of historically it's really an afterthought. It was not in SQL actually for 20 years. So SQL got standardized started getting standard in 1980s, and database standardizations take very, very long time. So the first standard was out in 1986. And there was no recursive capabilities until 1999. And even when there was, it's not a very elegant solution. Like if you've written SQL recursive queries, it's really ugly. So here is kind of an example of the type of question you would write if you were to try to understand this recursive parent of relationship, not direct subsidiaries, but also subsidiary of subsidiary, and sort of up to 5 hops, 10 hops, whatever, infinite hops. You'd write these queries that have a base case and a union, and you need to understand about these fixed points, computations. It's super ugly. It's really an afterthought. And actually, the way this was standardized kind of historically is that, as I will tell you, data log was kind of an alternative. People were doing a lot of research and work on in those years, in 1990s, to handle this recursion shortcoming of SQL. And this sort of syntax is all a borrowing of a specific data log kind of construct. But it's very ugly. It's kind of like a retrofitting something that's very specific and natural and elegant in data log into SQL, and people don't enjoy this. If you've written these, you kind of know the pain, especially if you also need to kind of understand the paths. If you want to look at the paths, not just to find if things are connected, but also return those paths and try to kind of operate on the paths and look at kind of inspect the paths. It gets really, really inelegant. So that's kind of how I'm going to motivate at this point in the tutorial about, okay, so you got these questions that you want to answer, and SQL is not a very good fit, then you want to go to another system, right? So that's one thing. And there will be other motivations that I give for why you want to kind of go beyond SQL, but those will be based more on the core needs of doing something more object-oriented, doing something more graph-based in terms of the modeling. That will come especially in RDF. Okay? So that's enough though to motivate Datalog, which is really, Datalog is a relational model, right? So you are purely relational still, but your query language is basically Datalog if then rules, which I will talk about, but it basically makes the advantage of Datalog is that you can remain in SQL, you can remain in relational modeling, pure tabular modeling, but recursion is much more natural through these if-then rules, and I'll show you some recursive if-then rules that overall kind of address this shortcoming, right? So the primary goal of Datalog systems is that this is the primary kind of feature that you get. You can stay in relational modeling, but you're extending your querying capabilities with elegant recursion, right? So this is an area that there isn't a lot of kind of systems, unfortunately, that you can use. There was a system called LogicPlug that got acquired. There's an open source tool, Souffle, but it's not really, I wouldn't go to production with it. It's, from my experience, at least teaching and using it in my classes, the support, etc., is not there. There is a company by the same people who built Logic Plus called Relational AI. That's probably one feasible alternative. And then there is a system that got acquired by Samsung, and you probably know this better than I do because I'm not directly in the sort of this RDF community directly, but it was an RDF system, so it's not a data log system, but they had a data log sort of layer over it to write some if-then rules for some reasoning and recursive reasonings that you might want to be able to do. So that also, as far as I know, is not available. But there has been systems, enterprises that internally built data log-like systems, and I think Bogdan could say here, Bogdan has built one, I think, as far as I know, some data log logic-based systems. Okay, so how would you answer some of these motivating questions that I mentioned earlier? So let me kind of, in the next 2 or 3 slides, I'll give you an overview of data log system. So you model your relations just as before. They're like, from your point of view, they're just tables. They're structured records in tables. In the logic terminology, these relations are referred to as predicates, but from our perspective, you still have tables. You still have a company table, a subsidiary of table, so on and so forth. The important part of data log is that it's a very different way of programming over these relations and querying these relations than SQL. Specifically, Datalog is a subset of this logic-based language called Prolog. And this was a very popular language. I mean, it's still around, but not as popular for AI applications, built for AI applications in the 1980s. And Datalog is kind of a subset of this. And this is how you kind of program in Datalog. You write these if-then rules where there's a head, right, with some variables and a body. And the meaning of this is the right-hand side, okay, for certain reasons. The if is on the right-hand side. So normally, intuitively, humans think of the if as the left side, and the implication then is the right side, but this is the reverse in Datalog. The right-hand side is the if, and the then is the head. So let me best explain through an example. So suppose this is your question. What is the company ID of Meta? Okay, very simple query. You can answer directly in a single, by querying a single relation, because it's in this company relation. Here's the data log rule you would write for this. So you write on the right-hand side, company C, and you give the string Meta to the right. So the C things that are not strings or integers, etc., they are called variables. And the strings are called constants. So what this is saying is that whenever there is a C, whenever there is a company record that have the name Meta, string Meta, so that's an equality match, then let's give the company ID the variable C. Whenever there is a C such that the name of that C is Meta in the company table, produce me an output for that C, okay? So this is basically, for example, in this case, it's going to match comp2. So there is a comp2 Meta. So because C matches to comp2, then it'll produce. So if this happens, then you produce a result, okay? So the comp2 gets produced in this Meta ID relationship, right? So this will produce this output on this table. So this is a simple example of how you write an if-then rule, right? So the equivalent SQL query would be written this way. So, just so you compare, right? But let's take something more interesting. Let's take this question. What are the customer IDs of direct investors of stock with ticker NASDAQ Google? So who are the direct investors of Google, NASDAQ Google? Right? So there is this, you need to essentially perform a join. In this case, you require a join because part of the information is in the stock table and part of the information is in the invests table. The if-then rule that you would write is something like this. So whenever there is essentially an investor C who is invested in a stock S, and so this is a variable I'm sharing here, and by kind of what that means is that I want an equality of these two variables. Whenever there's a customer C and that customer C invests in a stock S, and the ticker of that stock is the string NASDAQ Google, produce me the ID of the customer in the output. Okay, so it's an if-then rule. Whenever the right-hand side is satisfied, produce me a tuple on the left-hand side. And the meaning of putting two essentially relations on the right-hand side means that it's a join. It's actually for anything that's shared, any variable that's shared, you want an equality on those, right? So that's the meaning of this. So if there is a stock record S, NASDAQ, Google, and there's an invest record S, C, then produce me a tuple with that customer's C, okay? So just a note that whenever, like if you don't want to, if you want to ignore certain attributes in these relations that you're querying, you just put an underscore. It means like that's not important for my query. It's kind of like the way you would do projection in these sort of records that you're joining. Right, so the output of this would be maybe customer one and a bunch of other things, because customer one invests in stock one and stock one, so that's an equality of the S, has a ticker NASDAQ. So that's how you do perform joins, okay? But if then rules. That's the equivalent select SQL query as a comparison that I'm putting, but I'm not going to spend time on this. Let me just kind of demonstrate how do you do recursion and why. Let me back up my claim that recursion is a lot more elegant, a lot more natural in this if-then set of if-then rules, right? So suppose, let's go back to our question. Is YouTube part of alphabeting? And this was the question of finding not just for direct subsidiaries, but also indirect ones, 2-hop, 3-hop, up to infinite number of, all right? So here is how you would do this by defining a parent relationship, a recursive parent relationship in data log. So intuitively, logically, you know, a particular company P is a parent of C. A particular company P is a parent of C if C is a direct subsidiary of P. Either you're in a situation like this, or, and you know, so okay. So if a particular company P is a parent of C, either if C is a direct subsidiary of P, so you're in a situation like this. So YouTube LLC versus YouTube Kids, for example, their YouTube Kids is a subsidiary of YouTube LLC, and you'd represent that in data log with this. Whenever C is a subsidiary of P, then P is a parent of C, okay? So that's that rule. Or, and this is the recursive part, or it is the case that there is a sort of a parent of C, Z, and Z's parent is P, okay? So you're in this indirect situation, and this is the recursive part, right? And the way you would represent that is with this recursive relationship. So this kind of logically says it's a direct translation of this English sentence. Whenever it's the case that C has a parent Z and Z has a parent P, then P is the parent of C, okay? So there are these two rules. And if you define the same relation, in this case, I'm defining R parent of with two definitions. I've got this definition, and I've got a second definition. It means it's the or of those. So both of them, it's like a context-free grammar. If you've kind of worked with sort of programming languages, there's kind of multiple definitions of the same relation, but that means it's the or of these multiple rules, the if-then rules. So this is also true, and this is also true. Whenever you're a direct subsidiary, whenever C is a direct subsidiary of P, P is a parent of C, or whenever you're in this recursive case where C has a parent Z and Z's parent is P, then P is also a parent of C. Okay, so this is the two rules that you would write, and none of that with recursive ugly SQL. Okay, it's very natural. You're doing it, and you don't need to worry about how this is computed. Okay, that's kind of a very kind of technical academic topic. It doesn't matter. A data log system will take these two rules, very simple, very elegant. You're kind of like the essence of the relationship that you're trying to define is recursive, right? That means you just use it both on the left side and the right-hand side, and the system will magically compute you this relationship, right? So if you give this program computing the parent of relationship to a data log system, and this is your data set, not only from the first rule, it will find kind of relationships like this. YouTube LLC, Google Inc. is YouTube LLC's parent, Alphabet is Google's parent, but it will also find these indirect ones, and it will produce a table like this. Any questions?
So I'm not as familiar with data log. So when you just like write the two rules, like one above the other, would that automatically do the or between them for you?
Yeah, you just write, and it doesn't have to be like, you know, the order doesn't really matter. It's really very high level view definitions that you're making. And for a particular view, you think of the left hand side always as views. For a particular view, you could have multiple definitions, and the systems will automatically or things for you and kind of give you the natural interpretation that you have, which is kind of, there's different things that make you a parent of a company. right? And I'll define each one separately. You don't have to kind of, like, one advantage you get is you don't have to kind of merge everything into a single query that defines the entire relationship. You could say that, well, sometimes being a parent means just being a direct subsidiary. Sometimes it's something recursive, and I'll show you next example actually has 3 rules. So it gives you that kind of elegance and sort of flexibility. Okay. All right, so let me move on. So let me extend this running example. So suppose in addition to being a subsidiary of, you also had a second relationship between companies, which is the majority owner of, right? So some company can be a majority owner of another company, right? And now you have this question, does company X control company Y? Now in this case, you control a company either if you're kind of recursively a subsidiary, like a parent of it, or you're recursively kind of a majority owner of it. You control some others, like you're a majority owner of a company, and maybe that other intermediate company is a majority owner of another company, right? Maybe the middle one is Z, the other one is C. Then you could also control Z. So again, the nature of this relationship is actually 2 recursive things. You could say, X controls Y if X is a recursive parent of Y, or it's a recursively majority owner of Y. So the way you would write this in data log is these 3 rules. Again, you control it if you're a direct parent of X, Y. Sorry, this should be subsidiary of. Sorry, this is not parent of, subsidiary of. Or X controls Y if it's a majority owner of Y. Or X controls Y if through whatever means you control Z, an intermediate company Z, and Z intermediate controls Y. And you can put these 3 rules together. They're all producing U controls relationships. And it will essentially, again, you don't need to understand how this is computed at all. You don't need to reason as you do in SQL, how, SQL with recursives, you really have to reason about what the fixed point of those computations will be, right? This is kind of really high level declarative definitions of what controlling means, and it's very elegant recursion that you get, right? So there's tons of other things, obviously, in data log. You could do, for example, other standard relational querying like negation. Who are the customers who are not invested in Google? You got these sort of logical nots. You got filters, there's arithmetic, there's group by and aggregation. So you do actually get, even though I'm not showing you, you do actually get full SQL capabilities or majority of it, plus elegant recursion. Okay, so the takeaway is that data log systems, if you're in a situation where you want to stay in the relational systems, but you want natural kind of recursion, but you got recursive queries that you're having trouble to write with SQL, data log could come to your mind. The reasoning that you do in these cases, these recursive things you could do, you do them with these manual recursive if-then rules. And one nice thing is that it's view-based programming. So the left-hand sides are these view-based. So when you write complex business logic, it could actually really simplify your complex business logic. Right? So the first column of this table that I'm forming is this, and that's my final slide on data log. So I could take a question on data log.
Yeah, so is data log just more than syntactic sugar on top of relational, or you need both? I mean, relational has to be optimized for recursive traversals or something.
I wouldn't call it a syntactic sugar because it's a completely different, so it's got this different way of doing recursion. But if you're asking, is it kind of computationally equivalent? It is equivalent to current SQL because current SQL has recursion as well, right?
So could you technically slap data log on top of, say, Postgres as some?
Yeah,
or something?
you could, and there might even be some Postgres extensions that do things like this. Again, the best example I can give is this system called RDF Fox. Again, it was a closed source system, so I didn't really study it, frankly. But if you look at their documentation, it's an RDF system, and they put a data log layer over it. So they're using the RDF storage and query capabilities, but giving you a data log kind of view to do some of these if-then rules. Okay, so. It's not a system that I'm familiar, but people build this. And these layered systems are very, very common in data systems. Yeah. Questions? Yeah.
Are there different profiles of data log that might have different varying computational complexity, or is it usually just
there is? Yeah, excellent question. Let me take this offline. There's these extensions that can do different, very advanced things, like Semih rings, that they're more optimized for expressing certain machine learning computation, so on and so forth. And Relational AI team has kind of work in that space. And if you look at their documentations, I don't recommend looking at the papers. They're crazy papers, but yeah, the documentation certainly even mention these extensions. There is kind of extensions and different profiles, exactly. I think akin to kind of RDF profiles, if you will, like different capabilities.
Does Datalog separate federation with non-federated calls?
No, I don't know. I think that's a very orthogonal property of databases, whether or not you can handle federated things, etc. Those are really not at the core of Datalog. Those are kind of very system by system kind of properties of any data class, data system class. So let me move on in the interest of time to the second class of systems, property graph systems. So this is the second beyond relational system that I will cover. So these are systems that are based on Neo4j systems. So sometimes in databases, some areas start with a lot of kind of academic and research sort of work, and Datalog is an example of that. RDF is another example of that. And some systems, Neo4j kind of property graphs is an example, they start with one system. Right? So one system comes into the market, they have a particular data model and query language, and then it gets followed up with research, it gets followed up with other companies adopting it, so on and so forth. So you see both in the history of databases. IDS was another example where it was just one system that came about with its own data model and query language, and then there's research and academia, etc. They came together, standardizing it, so on and so forth. So both kind of paths happen. So this is a case where these are systems that adopt Neo4j's model. The data model is called property graph model, and the query language is essentially these query languages that are Cypher-like. Cypher is the language of Neo4j. Now there's other versions, it's kind of query languages like GQL, but they're all Cypher-like. Cypher is the core of all of these systems, right? So the focus of these systems, and now there's kind of more options here, both open source and in production. Again, like Neo4j, Kuzu, memgraph. Kuzu is the system we are developing. Tiger Graph, Janus Graph, Amazon Neptune. There's more options here compared to Datalog systems. And the focus is really provide a graph modeling to users and graph querying and graph analytics. So, these are truly graph systems. They really want to enable graph modeling, graph querying, graph analytics. The focus is really full on the providing features of allowing people to get a graph model over their records and do these paths and nodes and relationships. It's very explicit, and that a lot of the focus is on this graph modeling. So this is why I'm referring to these class of systems. They're truly graph systems. Like being a graph is extremely essential to the core capabilities that they provide. Right, so let's go through again the data model and the query language. So in our running example, these were your relational tables. And I showed you kind of a conceptual view of this initially before I showed you the tables. The property graph model is really very close to this conceptual model. So you kind of have this sort of node and relationship view of this. So you model your records as a set of labeled nodes and relationships and key value properties. But in some sense, it's also kind of very close to the relational model. Like the primary difference is you're kind of over here saying it is following at least my tabular sort of modeling, relational modeling of these records, except you kind of identify which one of entities and nodes and which ones are relationships and edges. That's what you do. Out of these records, you say these are relationships and these are nodes, but it's really close to the relational model. Now, people don't like me in the property graph model when I say it's actually very close. It feels very familiar to relational modeling, but I think that's objectively true. This is kind of like what is the minimum you could do to take your relations and give a graph view over them? It is the property graph model, right? All you have to do is that these records are nodes and entities, and these records are relationships, right? So in fact, this is not the same way you define in every system, but in Kuzu, we were very explicit about this. So you actually, if you're familiar with Postgres and sort of syntax, create table syntax, we really adopted Postgres syntax, except for your table definitions, you just either put a node or a relationship in front of it. So it feels like you're programming in a SQL system, except you're identifying and telling the system, these are my nodes and these are my entities, and that will be enough to get a graph view and a graph query language over this, right? Now, the original, I should make a note, the original property graph model by Neo4j you could also, it's more kind of flexible. You could put arbitrary key value properties on nodes and edges, right? So there you deviate from the relational modeling, because in relational modeling you cannot do that. But putting that aside, and when people go to production, according to kind of my experience talking to people, you don't generally put arbitrary things. You can kind of know you got a good control over the schema of your records, and if that's the case, you're really in the relational model with a bit of graph view over it. That's just enough so that you get this first-class notions of nodes, relationships, and path, and that's very critical for the query language, right? So here will be an example of the database. So if this is your schema, here could be your database. The red ones are your customer nodes, right? Just like your columns and values, you got these key value properties. Here is what is this? Invests relationship, and there's a key value property. So Alice invests 75 stocks in this stock GF. And then the blue nodes are your companies, and the blacks are subsidiary relationships. So that would be your view, logical view of your records. Right? The query languages of these systems are SQL-like. So Cypher is a very SQL-like. It feels like SQL-like. It feels like SQL. It's a SQL-like language. So here's a snippet of the three main clauses of Cypher. There's a match, where, and a return. So this is a query that's asking. It's really just like SQL. SQL was designed to be a language that felt like English. So this one also feels like English. So it's kind of asking if you kind of interpret at least the path in the match clause. It's asking for a customer A who invests in a stock S, where the name of the customer is Alice, and it's returning the ID of the stock and the number of shares. It's basically asking how many stocks has Alice invested in each stock that she's invested in. Okay, that's the question. And it's very SQL-like, because return is just like your select, where you do your projections, you define what you're returning at the output of the query. Where is exactly like SQL's where you have predicates. So here's an equality predicate, and match is where you do your join. So it's kind of similar to the from clause of SQL, but with a graph pattern syntax, right? So, and what it really gives you is this match clause. What's really special about these query languages and different from SQL is the match part, the from part. That's where you get this first-class notions of graphs, nodes, relationships, path. They could all be defined in the match clause. You could return these as objects as your query results. One important thing I should mention, I'm not sure on which slide, is that the results of queries, though, are not graphs. Results of queries are SQL. So that's tables. So it's another reason these are like SQL-like. I call these query languages SQL-like. All right. So, and again, similarly, the core of the new query languages like GQL standard is also Cypher. Okay, they're really based on Cypher. All right, so let's me demonstrate how would you address the same shortcoming of SQL, which is you need recursion. Let's take our running example query. Is YouTube part of Alphabet Inc? Right? This was asking for a path. The way you ask this question in Cypher is this. You're asking for a path P that starts from a company A, and you're saying that company A is connected with another company B through this subsidiary of relationship, but you put this star similar to string regular expressions. And what that means is that you're not only looking for a direct subsidiary relationship between A and B, right, where A is YouTube and B is Alphabet, but also indirect one. So the star means I'm looking for recursive relationships. I'm not just looking for a direct connection, but I'm also looking for 2-hop, 3-hop, up to either the system maximum hops or infinite hops. Okay, so it's this is again borrowed from the string regular patterns. If you remember string regular expressions, star in string regular expressions means match this character or the previous blob one or more times, or 0 or more times actually. So it's kind of borrowed from that, right? So this will return you actually. And the other thing is that you can bind the results of those paths into a variable. So paths are first-class citizens data types. So there is a data type called path, and you can return it in your query results, which means if you need to write an application that actually not only cares of connections, recursive connections between your objects, but also needs to inspect those paths, right? So maybe you're doing some kind of fraud detection, risk detection analysis, and you need to know exactly the sequence of things that connected one of your entities with another one. Because paths are first-class data types, you can return them and inspect them in your sort of query results. Okay, so but again, it's the output is a table, but the table can have these graph objects that you can return: nodes, edges, and paths. And Cypher also has, this is what I mean by they're very focused on giving users an ability to query graphs. They've got a ton of these query languages, have a ton of sort of other query language constructs to find, for example, other specialized recursive paths. You can find shortest paths. So different systems give differently, but like mangraph and kuzu, we give this syntax to find shortest paths or weighted shortest paths. You can define weights on your edges. These are all recursive computations, but they give you this very elegant syntax to perform these computations with a single sort of single word in your queries. And this will not find all paths after the star if you put shortest, but only the ones that have the shortest number of hops and things like that. Or you could do the lower and upper bound, like minimum and maximum upper bound lengths. And there's tons of other kind of advanced things about the nature of the paths that you find. So let me show you something that I think is important to understand about these systems, another kind of core querying capability, which is that they provide you with a very sort of elegant syntax to do these flexible joins. Okay, so I'm going to open what I mean by flexible joins. So let me first extend the running example. So suppose between your companies, between companies, you not only have the subsidiary of relationship, but you also have maybe a supplier of relationship and a majority owner of relationship. Okay, so companies can be majority owners of others, so companies could be suppliers of others. Okay, so you get these multiple different ways of connecting companies with each other. Now, suppose here's a scenario: you are at this financial company. Again, this is here in the financial domain, and you got a customer, Bob, who needs to divest from a company called Quantara. Okay, so there's a company for various reasons, for compliance reasons or something, you need to divest from Quantara, right? So here might be a question that you ask, which of Bob's investments are connected to Quantara? Okay, so maybe it might be the case, obviously, that Bob directly invests in a stock issued by Quantara, right? That might be obviously a direct connection, but it could also be looking for maybe, Bob invests in YouTube itself, and YouTube is a subsidiary of Quantara. That's an indirect relationship. But the nature of the relationships, given that I extended it with not just subsidiary of, but also other kind of supplier of, could be very mixed. So it could be the case that, Bob invests in a stock issued by a company who is a subsidiary of another company, who is a subsidiary of another company, or YouTube is a subsidiary of Google and Google is a supplier of Quantara, right? Google is maybe supplying, so you could be investing in a company that's a supplier of another company, which could be essentially major stakeholder on another company, which could be the subsidiary of another. Like the nature of the labels of the path, the different types of joins that you're doing could be very varied. It could be subsidiary of followed by another subsidiary of followed by a majority owner of, so on and so forth. Okay, so now if you just as a thought process, if you thought about how could you do this in SQL, it would be really, really ugly. Not only obviously that the question is by itself recursion, that gives you one challenge. It's also the fact that all the combinations of ways you could be connected to Quantara, your investments could be connected to Quantara. If you have essentially multiple sort of ways companies connect to each other, it just explodes. All the possibilities, all the kind of the combinations explode, right? But in a query language like Cypher, there's a very elegant way to ask this. So you kind of say, right? So A is your customer, Bob, right? You're interested in the case that Bob invests in a stock S, right? And that stock somehow through some arbitrary sequence of relationships, you just kind of remove the label. You just say, I don't care about the exact sequence of the join, right? I don't have that sequence of join in mind. Just search for it for me by all combinations, okay? All I care is that is there any connection, could be subsidiary of, majority owner of, supplier of, and any combinations of those to a company Q where Q is Quantara, okay? So that's a very elegant way of asking this hard query. And it would kind of really be impossible to, very, very difficult to write in SQL, right? You could also do, for example, you could also do kind of this, it's similar to string matching, regular expressions. You could also say, maybe you're only interested in subsidiary of and majority owner of kind of relationships in the paths that connect Bob's investments to Quantara and not supplier of. So maybe supplier of is fine, but you're just kind of interested in this direct corporate relationships. So you could do something like this. Again, you're interested in Bob's investments in a stock S, where S is through a sequence of just subsidiary of majority owner of relationships, but it could be kind of any sequence of them, right? You could kind of write these type of queries where you're kind of really, label string matching on the possible labeled join sequences. You could again get these nice elegant features. So whenever you're doing these path computations, the takeaway is that the query languages of property graph database, they give you a ton of features to essentially match paths, find paths, return paths, query over paths, compute over paths, so on and so forth. So again, in SQL, you'd have to manually write a lot of queries, and union them, it would be really ugly. You really need to go beyond SQL, beyond relational systems. And in this case, I think property graphs would be a very good fit. Now, this is essentially some modern applications we've seen from the user base of Kuzu kind of benefit from this. So we see people, for example, building RAG systems, where the core kind of architecture in a RAG system is that you're using an LLM as part of the system. And maybe you got some kind of corporate knowledge graph through which you want to retrieve records. So here's maybe some information about this company Quantara. And the question comes in, what are some corporate risks of Quantara? Like the way kind of what you try to do in a RAG system is that you go to your database and you want to retrieve some facts that the LLM does not know about. Now, in this case, you really want to ask something like this: fetch me all records about Quantara. You get an object. I don't care about its relationships, what the nature of the relationships are. Just tell me everything that I know about Quantara, and that's what you're going to feed to the LLM. You can ask this with this very flexible joins in a query language like Cypher. You sort of get this subgraph around Quantara, which has many joins. They're all different joins. Right? But you can ask it with a single query. You can grab that subgraph very quickly, give it to the LLM, and produce an answer. Right? So, these are kind of some modern applications that we see where this flexible joins is useful. Another kind of sort of feature that you get, I mean, it's not really a feature, and this is a little bit subjective, but I think kind of we see many users of property graph databases make similar comments, is that if you're searching for patterns in your data that you're naturally modeling as kind of graph patterns, okay? So maybe you're looking for 2 customers who have invested in at least 3 stocks together. They all bought the same 3 tickers, right? And maybe you're looking for is there some fraud going on? Why are these people buying tickets? Are they talking to each other? Or you're doing some kind of analysis like this. Or you're in a case like this, there's a customer who somehow is, through maybe indirect relationships, has a heavy stake in this company. There's another customer, and maybe you're interested to see, are there customers that have major relationships, also have some other direct contacts between them. Okay, so when you kind of ask that question to yourself, you are really asking about a graph pattern, and query languages of property graph databases make it kind of more natural to express these graph patterns. So a lot of people who build these fraud apps, for example, they kind of tell this as a benefit. So you're really, for example, in this query, this is the query that corresponds to the first pattern. You're really drawing whatever this between this graph pattern that you have between your customers and your stocks, you're really drawing in terms of kind of a sequence of paths. So that's another advantage. And the last thing that I want to say about property graphs is that they allow you to kind of, they have features that give you out of the box network algorithms or graph algorithms that you can just call, which could be important if you're answering some entity-oriented questions. So suppose this is your corporate network of subsidiary of relationships and maybe some other relationships between companies, and you're interested in a question like this. Who are my most important supplier companies? Okay. Or think of maybe another application domain where you got like social relationships between people, and you're interested in a question like this: find me the community of users that Alice belongs to. Or you got an ad campaign that you want to run, and you're interested in kind of which customers should I promote my campaign to. So these are all entity-oriented questions. And you could get signals from some graph or network algorithms if you're modeling your records and your data as a graph. So for example, there are well-known ranking and centrality algorithms to find important nodes in a network, in a graph, right? So you could, when you're using a property graph database, pretty much universally, they will supply you with a set of functions you can call to directly out of the box run one of these centrality or ranking algorithms. So that will tell you what are your important nodes, right? They'll give you community detection algorithms to find community of your users if you have modeled those users as nodes and their relationships in the graph database. Similarly, they could give you access to some influence maximization algorithms. These are all classic network algorithms or graph algorithms, and you could write them, for example, with a syntax like this. You match a subgraph, and then you can just directly make a function call, and you get PageRank. So you kind of found your, according to the PageRank metric at least, your central nodes or central users. So that's another property that you get, right? So what is the takeaway? This is my last slide. So the property graph databases should come to your mind when you truly need graph modeling, because they really focus on graph modeling, graph querying and analytics. Their kind of query language features are all optimized for that. You do recursion through specialized syntax instead of if-then rules. You got this clean star-based syntax, and there's a suite of them that you could do. Maybe not arbitrary recursion, but that's rarely needed. But the common ones, like find me indirect path, etc., they're all integrated into the query language as specialized syntax. And something that I think should be appreciated is that you could do this flexible joins that I mentioned, where you don't necessarily know the sequence of records that would join your objects with each other, your nodes with each other, but you could kind of delegate search of those possible records to the system as well by removing the labels from your relationships in your queries. And yeah, so the reasoning that you kind of do is through these manual path patterns that you find. Like the reasoning is like, is particular sort of company a parent of another company? Those are kind of, if those types of indirect reasonings you have to do, you kind of do it with these manual path constructs, right? So that constructs the second column of my table. Any questions about property graphs? Yeah.
So you'd mentioned GQL as sort of standardizing language. Do we feel like that's sufficient, or is there some?
Sufficient for what?
Well, I mean, is your company going to be adopting GQL?
We want to move to it. The core of GQL is Cypher. So we would like to move to it kind of more organically as kind of extend our Cypher capabilities. But right now we support Cypher. That's our core. Any other questions about property graphs?
What about the capabilities of SQL in terms of joins, if you may, like that might be just pertaining to the relationships, but in terms of whatever capability SQL offers, like is everything supported in, let's say, Cypher or even Datalog, or is it like is it a superset of that, or is it?
Well, I don't know if you are familiar with SQL Standard, but SQL Standard is crazy. SQL Standard is like 3,000 pages long document, and there's tons of things in SQL. But core SQL, when you think about the core SQL, is there, and that's not a coincidence, because query languages like Cypher or even SPARQL, they're all meant to be like SQL. Like they all feel and smell like SQL. They borrow kind of constructs from SQL. So the core of SQL is there in every high-level query language. But I mean, there's advanced things in SQL. You could do windowed computations, and they're not really good fits for Cypher, etc. So you don't get everything.
Basically, count of certain, where you want.
Yeah, those are very elementary. So all of those you get. So you should never question, if there's something very core, like, aggregations and group bys and, limits and sorting, etc. All of those are in every high-level query language that exists, not just for property graphs, but take any other kind of class of database systems too. They're very elementary. So they exist in every language. Good. So in the interest of time, let me move to RDF, which is actually the hardest or most advanced in terms of kind of introducing. So when I give lectures on these systems, I usually spend 2x time on RDF compared to, say, property graphs or data log, introducing the core data model and the query language because of certain very advanced things you can do in RDF, and I'll tell you about that, right? So these are systems that adopt the resource description framework or RDF data model, and their query language is a language like called SPARQL. Again, it's a SQL-like language, but with different ways of sort of performing the joins. And the focus is on, these are the class of systems that will come to your mind if you've got something very complex that you're modeling, something very heterogeneous, and you need a lot of modeling flexibility. And if you want to do automatic reasoning, right? So far in both of these systems, what I refer to as reasonings are not really true reasonings. You kind of manually write kind of these recursive things if you want to reason. Here, you'll get the system to do actually truly intelligent things, okay? So like you will get the system to do automatic things for you, okay? So let me motivate this with I need to change my application a little bit. So let's pick something more ambitious. Let's pick this project. Suppose you're at an enterprise and you're in this financial company working, and you're tasked with this job. You want to construct a knowledge base of all corporations, their sectors, securities, the regulations that they're subject, and the people who work in these corporations, so that you could feed certain other applications in your enterprise. Okay, so maybe some question and answering systems, so on and so forth, right? And you want to answer questions like this, how many companies are private corporations versus crown corporations? So in Canada, crown corporations are kind of like federal corporations. So they're called crown corporations. Anyways, my examples come from Canada because I live there, and Z was I could have given you away, like we don't say Z, we say Z. So some of these things will be kind of Canada specific. So here's an example. Or you could be interested in answering questions like, how many of your corporate companies in your knowledge base are subject to the offering memorandum exemption, which is the NI 45-106 regulation in Canada. That's about whether you need to issue memorandums before you issue stocks in Canada, so on and so forth. Okay, so or a question like, which federal companies are doing business in mining? Okay, so you got this high level, very broad questions you want to answer about all the knowledge you know about your corporations, their sectors, securities they issue, and the people who work in these companies, so on and so forth, right? So now the way I've been modeling a company in the previous examples is too simplistic now, right? So, a company with just an ID and a name is not enough. In practice, actually, there's actually, the company sort of structures or the kind of hierarchies of companies in terms of the way you would label them is very advanced. So, there's private companies for which you might want to store different information. There's public companies that have different regulations and different kind of structures. There's non-profit ones, there's crown corporations, all have different kind of structures and requirements. Even within just the private, there's different types of private companies. You could be a limited liability company. You could be a partnership, sole proprietorship company. Or, if you're a private corporation, you could be bootstrap, VC-backed, family-owned, so on and so forth. Okay, so this is, maybe this is a very ambitious project where you want that detailed level of information about the company. So you can no longer say, I've got a company node, and here are the names and the IDs. So that's not enough, right? What you really need is something, and because of the sort of the heterogeneity of all the information that you're sort of going to store, there's going to be, that's just the company related information. I didn't even get into sectors or securities, and there's tons of different kind of structures and securities as well. But the mere complexity kind of necessitates that you can't really go for something super structured, like a property graph or a relational system. You really need something that's more object-oriented in a way, that gives you a lot of flexibility in terms of the irregularities in the data and connections of the objects. So like, you really need something like this sort of conceptual hierarchy of what is a company, what is it could be a private company or a public corp or a crown corp, so on and so forth. So some kind of sort of even conceptual taxonomy of what things are. And obviously, plus, aside from what things are, you want the actual data, and to be able to say, this company is part of this hierarchy, and that is part of that hierarchy, so on and so forth. Right, so what you really want is something more object-oriented. You really couldn't go to a relational systems, and you need to go something to a beyond relational system. right? So this is a case where I'm motivating these beyond relational systems, not just through some recursive querying, but just the mere modeling capabilities of relational systems is too strict to model something as ambitious as this. If you want to have a single sort of database of all this information about corporation sectors, who works in them, and you want to answer the questions that I gave in the previous slide, you really need something other than a relational system, right? So RDF should come to your mind when you got that level of heterogeneity and irregularity, and that is the focus, one of the focuses of RDF, right? So let me introduce the data model. This will take a bit of time because it's a little bit more complex, but the data model consists of these things called resources, which are really your objects. And sort of compared to the property graph model, you also had these objects. They were just these nodes, right? But in the property graph model, those nodes are really just entities. Like those are really the data or the real world objects that you're storing. In the RDF data model, those resources, those objects could be entities as before, as in the property graph model, but it could also be these abstract things. It could be types. It could be properties that you store. Each thing, every concept becomes its own object, right? So that's the first kind of leap to getting this ability to model these complex things. So, you could have something like, you could be modeling as an object the company Quantara, which we also did in the property graph example, or Hydra Quebec is another company, or Google, etc. So those are your entities. But you also have as objects things like VC-backed corp, right? That's not a real thing. That's a concept, right? Or something like, company, okay? That's a concept. That's not really an entity. Or number of employees, okay? That's again a label of or an attribute name. That's not really an entity, right? But it becomes its own object, no different than how Quantara becomes its own object, okay? So this might be confusing if you're not that familiar with RDF. And that's kind of one difference that I want to highlight is that look at an object like company. So in the property graph model, we did model companies, but company was a label of nodes. It was not a node itself, okay? So company in the RDF model becomes a node itself, becomes an object itself, right? The other thing that is important in the RDF resources is that each one has a primary key, if you will, which is a URL-like string called an IRI, okay? This is a URL-like object identifier, and they have a particular form, and it's not really important for what I want to cover, namespace, column, local ID. They really like these URLs we put into our browsers. And you get a namespace. In this case, I'll just say GC for a made-up global corpse, which is the company that I'm assuming is developing this corporate knowledge base. And GC Quantara is just a shorthand for actually this long URL or IRI, right? But from our perspective, this is just a primary key that identifies it's unique per object that you store, per resource that you store, right? So that's the first part of the data model. The second part of the data model are these things called literals. These are just data values. So they're integers like 20 strings, dates, floating point numbers. They're just data, okay? They're not objects, and they're kind of treated somewhat separately. And then the core of the model are these things called triples. This is how you actually encode information and store information in these sentences, which are really the most elementary sentences in English in subject, verb, and object. Okay, so instead of verb, the term that's used is predicate, but they're really verbs, as I'll show you. Okay, so for example, if you wanted to store the information that Quantara is a type of a VC-backed corporation, then you'd encode it with this triple, GC Quantara, RDF type, and I'll come back to this. This is a standardized vocabulary that every RDF database in the world uses. GC, VC-backed corporation. So these are essentially resource identifiers you came up with for your application. RDF type is a global one. I'll come back to it later on, right? But it's essentially really following this elementary English structure. If you wanted to, for example, encode the information that Quantara has a number of employees 300, it's kind of a broken sentence. You would encode it as this, GC Quantara, GC num employees. This is a concept you identified. Okay, that's an application-specific predicate or verb. and 300 is a literal, right? So these are the sentences. And everything is a sentence. It's like speaking natural language. Everything is a sentence. Whatever information that you want to encode, you could just utter a new sentence. It just needs to be in the form of a subject, predicate, and an object, and you could insert it in the RDF. No real kind of sort of schema design in the sense of like, here are the exact structures of your records, and this is the information that you can store about each object. That, that you get a bit more flexibility, all right? So you can get a RDF database that looks like this, and I'm showing it in the form of a graph, where each resource becomes its own kind of object, like company is its own object, and you could say, for example, Quantar is a type of VC-backed corporation, which is a subclass of private corporation, which is a subclass of GC company, right? And you could also encode things like, Quantara maybe has number of employees 300. This is kind of a stretch in terms of a graph view because this is not really a node, it's just a value. But if you think of those also as nodes, those literals also as nodes, then you can see why people refer to RDF as a form of a graph database. But one thing that you get, for example, is that because your domain was really complex, you get a lot of flexibilities. For example, what I'm showing here is that, here's a company, right, that has a single CEO. Maybe this Hydro-Quebec has one CBO, Pierre Sabia, whereas Quantara maybe is in a co-CEO kind of structure, and you could just put another, as CEO record there. Like, if you wanted to have a third CEO, you could just utter a new sentence. You could say Quantara as a CEO, Alice or something, right? So, you get this flexibility in terms of what you can put into these data sets. Did you have a question?
Quick question on the, so if you wanted, I'm vaguely familiar with reification in RDF. If you wanted to define, say, a CEO for a given year, do you have the same approach in data log or liquid property graph?
Good question. So, no, I wouldn't say, like in data log, you really construct a new, probably predicate new table where you'd say CEO and a year, and it becomes its own kind of structure. Here, one problem you might have compared to property graphs, again, like one difference is that there's no natural way to put, properties on these edges. In the property graphs you do, so the reification really applies more to RDF than I think property graphs. In property graphs and data log especially, everything is a table, everything is homogeneously a table or a predicate, right? I would say it's more an RDF kind of technique to be able to add properties on your relationships, if that's a choice of modeling. Right. Okay. Another kind of irregularity you can model is, for example, again, these are two companies, but they have different types of properties. So this one, for example, is a crown corporation, so they get provincial designees. You could just add that. That's just another sentence. You could say Hydro-Quebec has this provincial designee, Michel something. And Quantara might have a number of employees that you store. Again, like you get a lot of flexibility of for which object do you want to store what information. It's really like speaking English and putting new simple sentences into your database, right? And you get a type hierarchy, like unlike property graphs or like and data log, you get a proper type hierarchy. You get the type hierarchies, class hierarchies are very object-oriented kind of modeling feature. Object-oriented programming languages kind of obviously have this cooked into them. But in terms of the data models, like property graphs or like relational models or data log, they don't have a type hierarchy. You can't get that level of object-oriented. So you can say, Quantara is a type of VC-backed company. Here RDF is a standardized kind of namespace with a set of vocabulary that you can use. There's also something called RDFS subclass of, that's another verb you can use to construct type hierarchies. So the two things you really use, it's more advanced, but there's other things, but the core two things is that with a type, RDF type and RDFS subclass of, you can provide essentially this type hierarchy. This kind of says Quantara is not only of VC-backed corporation, but it's also a type of a private corporation, kind of indirectly. It's also a type of a company, right? So just like, you do taxonomies in biology or something, you can have a taxonomy of what a company means. Okay, so you get this proper type hierarchy. Okay, I'll come back to these two namespaces. These are essentially standards that provide you with a suite of vocabulary, primarily verbs you can use in your triples or predicates in your triples that allow the systems who implement RDF to understand what you mean with your data, and that allows automatic reasoning, which is the next thing that I'm going to talk about, okay? But before that, I just want to show you something that I find interesting. Normally in any data model, you know, every data model has kind of like a, you know, when we teach data systems, we talk about the schema and data as if they're two separate things, right? So in the relational model, for example, you know, the schema is clearly the table names and the attribute names. That's what we refer to as a schema that tells you the structure of your records. And then the actual tuples you put into your table is called data. And usually you get these two different language features to actually define the schema and define the data. Okay, so like if you wanted to define the schema or in a relational system like Postgres, you have these create table statements, right? That defines your table name and the attribute name. And if you wanted to essentially insert data, you have other set of clauses like insert into. Okay, those are data specific clauses that you get. In RDF, this is different. In RDF, everything is a resource, right? So, you know, everything is a triple. So you homogeneously represent your data, like Quantara has 300 employees. That's kind of clearly data specific information. You encode that also as a triple. The way you encode kind of this type information about Quantara, that it's a type of VC-backed corporation, which was a table name in my relational modeling, right? That's also a triple, right? So what corresponds to a table name appears as a triple here, but corresponds to an actual data like 300 also appears as a triple. Okay, so there's this homogeneity, right? So suppose you wanted to do the following in this, you know, one advantage. This is kind of like an advantage of RDF in terms of this modeling. Suppose you wanted to say that every VC-backed corporation is subject to the Canadian NI 45-106 regulation, right? So in RDF, you just really put this triple. You say GC-backed corporations are subject to this. It's just another sentence, right? Now, let's imagine how would you do this in the relational system. It's not actually that easy. I don't even think it's really possible, right? So if you know, the problem is that that is an information that you want to put about the table. It's not about any of the records in the table. It is an information you want to put in the table, but you can't encode that directly into the schema. What you could do is you could say, you know what, I'm going to have a regulations table. And under the regulations table, if you've chosen to model VC-backed corporations as a table, I'll say this table name is subject to this regulation. But now you couldn't really join, like if you wanted to understand that Quantara is subject to this regulation, you couldn't really join Quantara's record, which is this, with this, because there's no common values, right? The common value is the record's value here with the table name, but that's not how you join things in SQL. Whereas if you look at RDF, they're kind of naturally connected, right? So you can, for example, here understand that Quantara is subject to this because it's a type of VC-backed corporation. That's a triple, and you can just do another join and get to GC and NI 45-106. So that's kind of the one kind of advantage of this type of flexible information modeling is that, you know, the schema and data are not really clearly separated in other systems, so you get this flexibility. All right, so how do you query this? So, you know, let's ask this question.
So in a prior example, why couldn't we just put VC-backed corp as like a company type as one of the attributes, and then just not call the table VC-backed corp?
You could, you'd have to do something like that, and then, you know, you're right. You can have different ways of modeling. If you've chosen to model the information that it's a VC-backed corporation, not as really a schema. Schemas are how you represent types in. There isn't real clear notion of a type in relational systems, but that's how you like the table names is kind of the types of your entities are encoded in the table names, right? So if you've chosen as a user, I was building the example that way. If you've chosen as the developer to model the type as the table name, which is the natural thing to do, right? Then you can't really put this information easily, right? You have to resort to things like, you know, I want to, like instead of structuring it this way, I want to have another column here, type, but that forces you to repeat that for every single tuple. And if you got like, you know, millions of records, you're repeating that just so that you can encode information about VC-backed corporations. Okay, so, you know, you are kind of you know, it's kind of like a hack from the example that I was building. Good. So let me just continue. So let's come to this question: which companies are subject to NI 45106? So the query language of RDF is a system, is a language called SPARQL. It's another SQL-like system. Again, from having taught databases for 10 years, every high-level query language looks like system, smells like system. They want to be like SQL. Sorry, every high-level query language looks and smells like SQL because, for very good reasons, by the way. But you know, you have actually even the same clause names. But the way you do kind of joins are different in these languages. So here, it's in some sense closer to a data log type of join where you put variables, like this is asking for find me all companies, right? Find me all C's, objects that are of type some T, and that T is subject to this regulation. And you're doing a natural kind of join by using the same variable twice, which is how you were doing kind of joins in data log, right? So that will find you over here, essentially every corporation that is subject to NI 45106. So it will return you essentially Quantara as well as Corpex. So that will be your output, right? So the way you join is different, and that might take getting used to, but it's really like a SQL-like language with the different ways of join. And you get filters, group bys, etc. All of these things are also borrowed in SPARQL, right? But let me kind of tell you about the automatic reasoning feature that you get in RDF systems. So RDF is kind of technology stack as RDF as a data model. That's a way how you encode information into these systems. But it also has several, and SPARQL is the query language, it also has several of these standards called RDFS and OWL and OWL profiles, so on and so forth. And those standards are essentially ways of doing this advanced automatic reasoning. All right, so you can think of a RDF data system not only as this database that stores your records, so that's what I'm referring to as the RDF core engine, but also as a reasoner as part of this. Okay, so let me show you an example of reasoning. So first, what is an RDF standard? RDF standard is just the standardized vocabulary that everybody in the world uses because, you know, some communities came together and wrote down what certain vocabulary or predicates mean, right? So and this is what kind of facilitates reasoning. So RDF type, for example, is standardized in this document. It is the way you identify, construct your type hierarchies, and you identify for each of your resource what is the type, right? And RDF subclass of allows you to do the type hierarchy by identifying which of these types or classes are subclasses of others, so on and so forth. Okay? They're all written down somewhere. And because this is a kind of a universal vocabulary that no matter which sort of company you work at, everybody, and if they're building an RDF application, everybody uses these terminologies. The systems that manage RDF data sets, they understand what these mean. So suppose this is your, let me show you this part of the class hierarchy where I've got certain actual corporations, you know, Corpex and Quantara that are VC-backed corporations, and that's a subclass of private corporation, right? So there is an inference rule that says that if X is this is kind of like in the standard. In the RDF standards, there is this inference rule. It's an if-then rule, right? Just like data log rules, but it's already written down, and RDF systems already know it. You don't have to, like in data log systems, you'd have to write this explicitly. In RDF systems already know this. You don't have to write this. The inference rule that if X is of type A and A is a subclass of B, then, as you'd expect, X is a type of B as well. So even though you have not encoded this triple saying Quantara is a type of private corporation, systems can automatically infer this. So if you ask this question, for example, give me all private corporations, right? You're asking for a triple of RDF type private corporation, and there's none of it here, right? Private corporation is only as a subclass of it, doesn't have an RDF type. But because of this inference rule, right, an RDF system will actually return you Quantara and Corpex because they will reason, because they understand the meaning of RDF type and RDF subclasses, even though the triple Quantara RDF type private corp does not exist, right? There is this indirect sort of inference rule that the system already knows, so it will actually give you what you expect, which is that Quantara is actually a private corp and Quantara is actually, Corpex is actually a private corp, right? So let me give you another example. So suppose you modeled this controls relationship. Quantara maybe controls corp X and corp X controls corp Y. Now, in the data log example that I gave in the beginning of the tutorial, I had to write these manual kind of recursive rules to reason that Quantara also controls corp Y indirectly, right? I had to write these recursive rules. Now, the way you would do that in an RDF system is that you would instead just say controls is a type of owl transitive property, right? You don't have to write, like you just say the nature of this controls vocabulary that you have is that it's a transitive property. So what that tells the system is that if you see chains of controls relationships, right, you can also infer that Quantara actually also controls corp Y, right? You don't have to write additional rules for that, right? So if you ask this query, what are the companies that Quantara controls? An RDF system that implements OWL, right? Its reasoner is sophisticated enough that it understands what OWL transitive property means. Will actually, will actually return you not just corp X, which obviously there's a direct relationship, right? But also corp Y, because it will reason. So this is what I mean by this automatic reasonings that you can do in RDF because of this inference rule in some standard. It says that if you have a predicate, like say GC controls that's of type OWL transitive property, and X controls A and A controls B, it's an if-then rule, then X controls B. Okay, that's written in the standard somewhere. All right, so tons of other very advanced sort of reasoning features that you could have in RDF, like OWL symmetric property, OWL same as. You could actually, if you're, it's like a lawyer writing down the definitions of everything and kind of saying the nature of the relationships between everything. You could do this level of kind of modeling that will allow systems, reasoners to actually infer facts that you're not directly entering into the system. So this is what I mean when I say that RDF, if one of the focuses is that it can do advanced automatic reasoning, that a property graph system or a data log system in which you'd have to do your reasonings manually with your queries or with your data log if-then rules, you kind of get the system to do these things for you automatically. I didn't get into it, but you could also do flexible joins here. And there's some not very nice, I think, objectively regular patterns. If you want to do some kind of graph querying, you know, they're quite weak. And so it's doable, but it's kind of like an afterthought as well. So they're not kind of as elegant in terms of the graph querying that they can do. Okay, so that completes my sentence, my table. One last thing that I'm going to say is that I had in the Kuzu YouTube page a playlist where I get into a lot more detail about these systems, except data log. It gets into the property graph and RDF and their pros and cons and at a more detail. And, you know, we'll be around as the Kuzu team here. So you could find me throughout the conference. I'll be here until Thursday. Okay, thank you very much for listening. Yeah, question.
Great talk.
Thank you very much.
Have you not found enough benefit for going RDF for Kuzu? Like, don't you have needs for those things that you said are advantages?
Good question. So when we kind of started Kuzu, there was at the core of the system, we wanted to have this feature called RDF graphs, right? But over time, we understood it really complicated our development. So what we are doing is something along the lines of what Neo4j did, which is Neo4j has this neo-semantics, which is kind of this plugin to the system that allows you to at least move data, take RDF turtle files, maybe move data into Neo4j and give Cypher over it at least. So our feature RDF graphs was similar. Currently, it's not in the system, but we plan to bring it back as a plugin, so you could at least move the data. But we don't currently, it's not in our roadmap to do automatic reasoning yet. That's not in the anything. But basic querying of your triples with a Cypher syntax existed in Kuzu. It's now kind of, we took it off so that we could bring it back as a plugin instead of doing it at the core of the system. All right, maybe at the back.
We have some virtual questions. How does your data log engine handle recursion over large cyclic graphs?
So good question. So Datalog adopts this notion called fixed point computations, right? So I couldn't get into it right now. It's kind of like the way SQL does its recursion. SQL recursive computations are also these fixed point computations. So cyclic graphs are fine as long as you're not running into kind of infinitely many tuples. Like, if you're looking for all the paths between a particular, if you get a cyclic graph and you're looking for all the paths, if there's a cycle, that could be dangerous because there's infinitely many paths because there's a cycle. So as long as your data is in a way and your query is in a way where you're not running into infinite output producing problem, they just handle it sort of. And the important point is that as a developer, you don't have to understand it. They're kind of optimized to do those types of recursions for you in an efficient way. Yeah.
We have one more question. Is control a reserved keyword in this setup?
What is that?
The
Sorry.
word control is a reserved keyword in this setup.
Reserved keyword. No, it was a application specific vocabulary I picked to describe when a company controls another company. It was completely application specific. It was not reserved, right? It was in my running example basically. Question.
Open world assumption, does that apply to data log and label property graph?
No, they're closed words. They are under the closed world assumption. So all your facts are whatever is in the database, and beyond that, they won't reason. Okay, that's an assumption only some RDF, not even every RDF system will do. Some RDF systems might do that. Yeah. All right. Okay, one more question.
So the example that you use with the corporations and then the relationship schema, wouldn't it be really that you would have just
I missed the beginning of the
regarding your relational schema with the what was it,
VC-backed corporation, yeah.
I mean, in a real system, you wouldn't have that as a table. You would just have a corporation with corresponding classifiers, which just means that the transformation from your relational schema, the RDF schema, is a bit more complicated because the classifier, which then actually tells